Yes. Good evening, everyone. So, in the previous session, we discussed some few programs based on the dynamic programming. So we are left over with one more important interview and coding section program called Coin Change. Okay. So after completion of this, suggest with some one program. So Ratin Maze program actually asked in previous year HackWithInfy. Okay. So that is from backtracking actually. So after explanation of that one, today I'll end up the hack with Infi classes. Okay. So after completion of explaining that program, so go through the programs based on that n queens. Okay. So permutations of string. So all those are are a similar model. Okay, of backtracking. So with the program, whatever we are going to discuss in today's session, with that, so you can easily understood those programs. Okay. So fine. So already coin change program you observed in greedy approach. Okay. So there minimum number of coins we need to return. Right. Okay. You observe the greedy way of thinking by traversing in reverse direction. So all that. Right. Okay. So but now here. It's a different problem statement differs from that greedy approach program. Okay, so what is given here? Let us see in detail now. Okay, so observe you are given an integer array, coins. Okay, representing coins of different denominations. Next, so here coins means it's different. Actually, in greedy approach program, so we taken coins. So whatever the currency we have in India, so all those values we taken in the coins array. Okay, but here it's not the same. Actually, some coin values passed. Okay, uh, so coins taken into an array, and so that array passed to the method. Okay, and after that, apart from that, an integer amount representing a total amount of money is also passed. Okay, so there also you observe this. Okay, this is similar. There is no change regarding this argument. Okay, in greedy approach also you observed amount variable, but there we observe this variable as n. Okay, in n variable, so we have amount over that, but here directly some amount variable is given. In that we have some total amount of money, guys. Okay, next, return the fewest number of coins that you need to make up the amount. Okay, yeah, 1 minute. One more uh, program is there. Wait for 1 minute. So I'll open it. So that is asked in previous year. So that is ways to make coin change. Okay. So I think this one. Observe here. This one asked in 64 companies. Like okay. 64 companies entered this one when compared to the all remaining programs. So this is very important. Okay. Ways to make the coin change here. So this is what I have to explain. Okay. So fine. Listen. I think there actually fewest number of coins we need to return. So actually that one we already observed in the greedy approach. So now here how many ways we need to find, okay, to return some particular so change. Okay, observe the problem statement. You can understand it. I changed the platform here from lead code to the coding ninjas here. Okay, so you are given an infinite supply of coins of each of denominations, the D naught, D1 to so on up to d of n minus 1, you need to figure out the total number of ways, okay, in which you can make a change. So for value v. So here value v is given in that greedy approach program, some amount n variable is given. So there we need to find the fewest number of the coins, guys. Okay, but here we need to find the number of ways. Okay, there so it differs the problem statement. Already returning fewest number of coins I explained in the greedy approach, right? That's why I changed it. Okay, so problem to the coding ninjas here. Actually, in lead code we have returning some fewest number of coins. Okay, so this is important actually when compared to that. Returning fewest number of returning coins instead of that. So return finding the total number of ways, okay, to in which we can make change for value v is the important one. Okay, that's why I changed the platform. I hope so everyone understood this. Uh, so after completion of this, gone through that, okay, lead code program, and next of all, so try to design it. Okay, that is also from dynamic programming, guys. Next, using coins of denomination. So from the print zero if change isn't possible. Okay, so fine, observe the sample input. And so here coins, these are given, guys. Okay, coins means don't think that they'll give you just 1, 2, 5, 10, these only. Okay, just like in greedy approach. They may pass any value. Okay, some value is printed on the coin. That's it. And next, so the total amount, so 4 is given. How many ways we can return? So change to the 4 here. That is the problem statement here. So all ones we can return. Okay. Two ones and 1 2 we can return. 1 and 3 we can return. So or else 2 and 2 we can return. Okay. Totally how many ways are there? 4 ways were there, guys. Okay. Now this is what you need to print onto the output screen. So actually in the lead code problem statement, they asked you to the count of fewest number of coins we can return to the change. So here the fewest number of coins 1 3 or else 2 2 you can consider. So you need to return some value 2. Okay. So that is the difference here. Next. So here let us take sample input 3. Here the coins are 5 3 2 and next of all so the amount 1. It is not possible because 1 rupee coin is not there here. Okay, so in that scenario we need to return the 0. Okay, I hope so you understood. Okay, and so in dynamic programming you all know first of all we should design recursive solution. So afterwards we should convert into the dynamic programming tabulation method, guys. Okay, first for designing recurrence, okay, or else designing recursive solution, what steps we need to follow here? So check everyone at once. So first thing is expressing a problem in terms of indexes. Okay, so here we have only one array. Okay, so first of all we should take the calling function and next of all the called function. Okay, so for the last index, so in recursion we start working from the last index. Okay, so in iterative approach we start working from the starting index, right? Okay, next, so after that, here also you are going to observe the same thing at some particular index. Okay, it is possible to pick some particular coin or else it is not possible to pick some particular coin. Okay, same thing you are going to observe. There is no change in the second point here, but third point you can change. Okay, so here what we need to do? We need to collect. For suppose on picking some particular coin and moving on, not pick and pick, we may get the result. We may get one way. Okay, or else on not picking and next of all, so pick and not pick, we are going to get some way. Okay, so we are going to return the return results. Okay, if it is possible to if we are getting some way means we are going to return one. Okay, to either pick or else to the not pick. So those values we need to add here. We need to continuously add how many ways were there. Okay, to return so change for the particular value here. So that's why what we need to do here is we need instead of so the maximum we need to do this. So find sum of so these possibilities. Okay, after returning some result to this. Okay, if it is possible, if we one way is generating means so we are going to return so that, and after that we need to sum those results, and finally as usual this one. So what base condition so we need to take here to stop the recurrence? Okay, all these let us discuss in detail first. So let me complete so this one, that is expressing problem in terms of indexes. Okay, calling function and call function I'll explain. Afterwards, so these two I'll explain, guys. Okay, with the sample example. All these 3 points I'll explain with the sample example. So fine. Observe everyone. So here already, so they given one function called count ways to make a change. Okay. So to this function, so this one denominations array passed and next of all, so the value passed here. Okay. Now we need to calculate here. Okay. Calculate and so find how many ways are there to make the change. Okay. So the very first step is we need to take the calling function here. So we need to work with denominations. I'm passing that, and next of all, so we need to work with the value. Okay, and so here we need to pass the last index. Okay, so last index I'm passing here length of denomination, so the minus one. Okay, now let us go for defining so the called function here. So that is define f of denominations. Okay, next value, and so index I'm collecting into the so I variable here. Okay, so fine. Now I'll explain with the help of some sample example. Okay, all of you observe carefully. So we have some coins array or else a denominations array. Okay, let me maximize this one. So next of all we have some value with us. Okay, so that is let us take some 5 rupees, guys. Okay, so this is the value we have. So the total amount, guys. Okay. Next, what do you observed in greedy approach program? Okay. So we are at this index now. Now I is pointing to this index. Okay. Uh, First, we should check so whether this value, what are the denomination value, if it is the less than of some particular value or not, then only it's possible to so pick that one, right? Okay. So the same thing you are going to observe. Observe, have a look, everyone. So if denominations of I, if it is less than or equivalent of so the value, yes, it is true, right? Okay. So initially that is 3 less than or is equals to of so 5, true. What we can do? Yes, we can pick this one. Okay, we can pick so this particular so coin here. Okay, so means for pick. Might be if this not condition not executes, okay, we need some value, right, for adding. So that's why pick initially I'm taking to 0. So what I'm doing here is we need to generate so the recursive function call here. Observe everyone. So denominations value I'm passing as it is, okay. Sorry, 1 minute. Denominations I'm passing as it is, but on picking some particular coin, okay. So value has to be reduced, right? Yesterday you observed knapsack. Similar type of recursive function called generating you can observe here also, okay. After collecting some particular item, so we reduce it the knapsack capacity, right? Okay. Likewise, on picking some particular item, uh, picking some particular coin here, we need to reduce the value here. Okay. So how we need to reduce the value here? Observe value. We need to subtract with the denominations of I guys. Okay. So consider D for denominations, V for value here. Okay. And so one more thing, so we need to do here. So that is either is it required to update to the previous index or not? We need to check. No. So might be for suppose consider if value is 6, okay, on staying at the same index, so on returning some 3 again, coin 3, we are going to get one solution, right? Okay, we are going to get one way. So that's why we need to stay back at the same index here, okay, while picking some coin. This is the step we need to remember. This is the change. So when compared to the knapsack program here, okay. In knapsack, what we do on collecting some particular item, we update index to the previous position, but we do not perform like that, okay. So in the coin change. So I hope so it's clear for everyone now, okay. So this is about pick. Next. So next, let us talk about not pick. Okay. Okay, fine. So here, after collecting this, again we are going to check. So whether what is the leftover value now? It's 2, right? Okay. 2 is it less than or is equals to 3? False. Okay. Uh, so now listen. Let us take so this. Next of all, after generating so the recursive function call here, so denomination is still 3. So but value is updated to the 2 here, right? Okay. Remember, after evaluating, so this one value updated to 2. 3 less than or is equals to 2. Okay. So it is false. Okay. It is not possible to pick, right? Okay. If it is not possible to pick next time, so what we need to do? We should generate so the another function call, right? Okay. So that one we call it as not pick. Okay. Listen, not pick. And here, if we are not picking, so means so now it's required to update to the previous index here. Okay. We should update to the previous index here. Simply, we should generate recursive function call, right? Now there is no updation of value. Directly value we need to pass as it is, but index we should update to the previous position here. Okay. So this is about possibilities. Okay, in this program. So pick and next of all, so the not pick. I hope so. You clearly understood so about this at some particular index. Okay, either by picking some particular coin, we may stay at the same index. Okay, or else it is not going to be possible to pick some particular the coin. Okay, and next to this, what we need to do by moving so like this. Finally, if we reach to the destination. So after picking some exactly if picking values matches with the value, okay. So then we are going to return result some 1, okay, to either pick or else so the not pick. So those results we need to add here, okay. This is the third step. So pick and next of all, so not pick we need to add, okay. So up to here, I'll complete the program. Okay, already observed here. So, but in coding screen, I'll complete. Afterwards, I'll explain the base condition. Okay. Okay, so fine. Listen. Yeah. So what I said, first of all, let us take so the not pick. Okay, if we are so the not picking means we should generate so recursive function call. So like this denomination. So value we should pass as it is. Just we should update so to the previous index. We should generate function call to the previous index. Okay. So or else if we are so the picking. Initially, if condition not going to be executed, it is going to consider pick variable value as 0. Okay. So now observe if denominations of particular position, so value, if it is less than or equivalent of so the value. Okay. So then we can pick that particular coin, right? Okay. And we need to stay back at the same index. So observe that part, everyone. Pick is equals to f of denominations. Okay. And at the time of picking some particular so coin here, that value we should reduce, okay, from the total amount. So the same thing I am performing here by reducing the total amount. I am going to generate the recursive function call now. Okay. Observe here denominations of I, and so now we should not update index. Okay, so to the previous position, we should stay back at the same index. Next, so either to here or else to here. After reaching to the base case, okay, you are going to observe next of all. We are going to return one. Okay, uh, if we are going to return one here, okay, so we are going to add zero, and so that result we are going to return to the previously generated recursive function call. Okay, so either to here or else to the here, we are going to return so the result called so pick plus so the not pick to the previously generated function call. So these values are going to be returned, and finally again and again, so those values will be added. Okay. So results, multiple results, whatever we are going to get will be added. Okay. So fine. Next, now let us focus on the so base condition here. Okay. So I'll explain. Listen now. So base condition we should take so for I value 0, right? Okay. Whenever so the I is pointing to the 0 in that scenario, so we need to focus on the base condition here, right? So for suppose let us consider that so we have 2 rupees at 0th position. Okay, I value is 0, 0 index mo 0 index so coin I am taking as 2. Okay, now so value, so we have leftover is 4. Okay, leftover amount is 4. So is it possible to return so that we are going to get some way? So means on reaching to the zero index, definitely, because so here zeroth index so contains 2 rupee coin, right? Okay, total amount we need to make, okay, is 4. So the leftover amount we need to make is 4. Okay, on returning some 2 rupees coins, we can return it, right? Okay, and so I hope she understood. It's possible. Next, for suppose let us consider. So let us take so this at zeroth index. So we have value. So coin 3, and so we need to make so the value 4 here. Okay. So how is it possible to make so the 3 rupees? 3 rupees we can return, but we are still left over with so 1 rupee. We need to make one more rupee. So it's not possible, right? Okay. So these two base conditions. So we should think here. Okay. So means this is the denomination. So Ari, right? Okay. If denominations of 0th position value, uh, so that is value, whatever the value we have. Okay. So on dividing value with so denomination of zero position value. Okay. So definitely it's possible. For suppose here if we have so the value 6, okay. So 6 on modulus division of 3, definitely it's possible. But here I'm taking so the value 3 guys, okay. I hope so you understood. So as 4 on dividing with the 2, it's possible. So it's matching with 0, we are going to return result 1, okay. But on taking so the 4 modulus division of 3, it's not matching with the 0, okay. So I hope you understood. Uh, like this, we are going to get the final result here. Okay, after reaching to the zeroth position, so whether we are going to get one way or not. Okay, so we are going to understood this on returning so that result. So it is going to be added and returns to the previously generated recursive function calls. Like this, so it works. I told you by taking some recursion tree, so you can understand in detail. Already for some programs, I taken so the recursion tree. Okay, you to also take recursion tree by taking some sample example, and so you can understand in detail. Okay, so next, let me complete this and check whether so it works or not, or else we are going to get TL error. Okay, so wait for 1 minute. But suppose if I value reaches to the 0, okay, so here we need to check whether value on dividing so with denominations, okay, of 0 position, if it is, you can take so 0 or else I, there is no problem in it if we are getting so the result 0 or not. If it is 0, okay, so we are going to get a return so 1 here, okay, or else it is going to return so the 0, okay. So I hope you understood this. Okay, let us check now. Okay, let us run first of all. Base cases executed. Let us submit. So yeah, we got time limit exceeded here. Okay, hidden test case only one test case passed. Okay, so now we need to optimize it. Okay, yesterday so you observed knapsack program, right? Okay, so how I made conversion into the so tabulation method. So you observed in similar way. So we are going to make conversion here. So here we have one array, guys. Okay. So denomination array. So with that denomination array size, okay, the denomination array size we are going to consider as a row size, okay, and so the different values, okay. So from 1 rupee to that given value, we are going to take all those values in columns, okay, and afterwards we'll start so the filling values here, okay. So first, it is the first change we need to make. So the calling function, right? Instead of so passing index, last index, we need to pass so size here. That one I'm collecting so n. Okay, in n variable. Next, now I'm creating some 2D array here. Okay, initially we take so the zeros in all memory locations. So what I'm saying here in the column, so we are going to take so values. Okay, from 1 to n, from 0 to that particular value. So we are going to take it in columns. So just like in knapsack. Next. So here, next one, rows we are taking for, so the, okay, 1 minute. Okay, fine. Next. So in rows, we are going to take, so the denominations, okay? Values here for I in range of, so the n, okay? So first, so I'll explain this, okay? So conversion of base case, okay? So observe everyone. Afterwards, let us see how to make conversion of, so the remaining part. For suppose, let us take, so our example only here, okay? 1, 2, 3, right? Okay, we have totally 1 rupee coin, 2 rupee coin, and 3 rupee coin. Okay, so value is 4, right? So what we did, we taken so the all values 0, 1, 2, so 3, 4 in columns, right? We taken so the value plus 1 means it is going to generate up to value, right? So initially we filtered so the all values, all memory locations with zeros, okay? So but I'm not doing that now. So I have to do one thing, 1 rupee. So zero index, first index, and next of all, so the second index. Okay. So these are the row indexes, and 0, 1, 2, 3, 4 are the column indexes, right? So now from when onwards, so it is possible to so pick this one. So this 1 rupee coin, is it possible to so pick here? No. Okay, because it's a 0 rupee coin. Okay. So here it is going to be filled with 0. Okay, but 1 on dividing, so the 1 it's possible, right? Okay, 2 modulus division of 1, yes, it's possible. 3 modulus division of 1 possible. 1, okay, 4 modulus division of 1, yes, it's possible. We are return if it is possible to divide, what we return? So 0 and 1 only, right? Okay, so the same thing you are observing here. 0 and the modulus division of 1, it's not equivalent. Okay, we are going to get so the 0. Next. 2 rupees. So again, it's not possible. And likewise, it is going to be filled. So the next rows here, uh, we do not want to fill each and every for each and every program. So here in the backend, it is going to be filled in the last position. So we are going to get the result and it will be written. So just I'm showing you the conversion of how to convert recursive solution into a tabulation. Okay. After it's gone through this recursion tree and next of all, so the table filling. Just I showed you the previous class also I showed you how to so convert the base case here. Okay. So from this position onwards, right? Okay. Here onwards, actually values are going to be filled. So let us see that one. Let us see that part now. Okay. Observe everyone. So we are taking for columns only, right? For j in range of, okay. So value plus one. This is for columns, right? Next. Now I am removing. So this we are at 0th row, guys. Okay. We are at 0th row only. Next. So what is the condition we need to use? This one, right? If on dividing, so that particular value, okay. So with the denominations of so 0. So then only we returned 1 here, right? So the same condition I am taking so here. So but in place of value, we need to take so the z different values, okay? Different values we are getting into the j variable, right? That one we need to check whether it's divisible or not. If it is divisible, so what we need to do? Earlier we returned 1 and so 0. But what I said in DP, you should so make conversion like this. 1 minute. So in place of return keyword, what I said. So we need to take so DP here. Okay, this one not required. DP of 0 row is fixed. So the columns are changing 0, 1, 0, 2, 0, 3, all this. Okay, we need to fill so the result with 1. Okay, this is the first step. Okay, base condition conversion. Next of all, we should focus on converting so the remaining steps. Okay, let us complete so this part now. Okay, observe everyone. Already we filled it so the zeroth row, right? Okay, it's not required to work with that row again. So directly I'm starting from the so first row for I in range of 1 comma uh, so n here, and next for j in range of value plus 1. Okay, after this, what is the next step? We should take so the entire so program inside so the for loop of j, right? So this is the next step. Next, what I said, in place of so the function call and it is not required to work with these parameters. Okay, we need to take so the dp array and so indexes we should take in subscript. Okay, so here also it's same wherever so you observe so the value in previous session also you observe this in knapsack wherever you observe the knapsack capacity in place of that we taken j variable. Okay, so here in now j variable we are collecting so the different values, right? In place of values, okay, we should take so the j variable. Remember this, in place of value you should take so the j variable. Next, so here also it's the same, in place of denominations I'm taking dp, and in place of value we need to take so j here. Okay, this one it's fixed, so row subscript is fixed, so the column subscript we need to change now. Okay, so with this one j minus denominations of I. Okay, so I hope you understood there is no change in the so I index. Okay, only we need to change so this one. So next, so again here in place of return keyword, we should take so dp of ic, okay, and should collect the result pick and not pick. And finally, after completion of so the both the loops, okay, we need to return so the result. Okay, result is stored in n minus one index. Okay, this one is regular. So array index, right? Okay, array next it ends with the size minus one, and next of all column position. So we need to take so the value here. Okay, we created with value plus one in value position. So we are going to get the result. Okay, so this is a coin change program. So easiest one. Okay, it's not difficult. Easily can so write and explain in front of it. So wait 1 minute. So we got an error, unsupported operand types. Okay. Yeah, fine. So here just we take an I minus one. That's it. We forgot to take another parameter. So fine, now it's executed. Now let us submit the code. Check whether so all dash is passed or not. As all dash is passed, we taken low time only now. So the runtime 139 milliseconds. It's good. So fine. I hope so. Each and everyone understood. So this. So please gone through for 2 minutes. Okay. With this, I'm ending actually dynamic programming still. So we have some more so programs, so important programs were there. You should so you just gone through with the help of this knowledge. Okay, so it's not possible to discuss so the all programs within this short span of time. I hope you understood. That's why only so I'm explaining so the models here. Okay, so with these model programs you have to gone through at least. So these are helpful for your for interviews also, right? Okay, if I just go for explaining some coding questions or whatever asked in some HackWithInfy means might be may not get so that, and it is not useful for the interviews also. Okay, but so these sometimes you are getting in the coding section, and next of all it's definitely useful for interviews also. That is the reason for picking these programs and explanation. Okay, hope you understood. So please gone through for 2 minutes. So next, so let us see one program from backtracking. Just like so in these programs, dynamic programming, okay. So we are so going to get number of paths, okay. So but here in those paths, so what we did? So we collected so either max or else min results, okay. In string programs you observed. So here we taken so the sum, okay, in coin change. So but if you want so the all the results, okay. Uh, so in all those paths, then we go for so preferring. Then we consider so that one as backtracking. Okay, in that scenario, you need to backtrack if you want all the results. What operations you need to perform so that while backtracking, all these concepts you are going to observe with one program called Ratin Mage. Okay, so in a similar format, so you can understood. I already said n queens are next of all. So the remaining programs, permutations of string, whatever it may be. Okay, similar structure you can observe. So the all remaining programs. Again, it's not possible to discuss all programs. So just one program, important one, and so asked in previous so year also. That's why I'm taking so that okay. So check Ratin Maze all parts. It's this one Austin. So 60 plus companies. So actually, this one changes from platform to platform. So the problem statement so changed here. Okay. So actually, this program not asked this way. In this way, actually not asked. So in the hack with Infi. So in geeks for geeks, we have so one problem statement. So observe this, everyone. In this way, actually, it's asked in the previous year hack with Infi. Okay, that's why first of all I'll explain this. Okay, again, just like similar, you observed coin change program, right? It is present in lead code and next of also the coding ninjas. Okay, problem statements are differed. Small changes will be there. So by adopting those changes, check whether you can understood or not, you can execute or not. Okay, so practice it. Next, so here I'll explain from this one, Gigs for Gigs, and I'll show you the solutions from so worker tech and next of all, so the coding ninjas also at the ending if possible. So listen. So what is the problem statement, guys? Consider a rat placed at positions so the 0 and 0, okay, in an n by n square matrix, okay. So here square matrix is given, name is maze, okay. The rat's goal is to reach the destination n minus 1 and n minus 1, okay. And the rat can move in four possible directions. So those are up, down, left, and next of also the right, okay. So fine. So matrix contains the only two possible values. 0 indicates the blocked cell through which the rat cannot travel. So 1 indicates a free cell that the rat can pass through. Okay. So observe the problem statement clearly, guys. First of all, everyone. Actually, so here it's given up, down, left, and right, right? But here in Worker Tech platform, so you can check, it's given that only rat can move in two directions, down and right. Likewise, you can observe the changes from platform to platform, okay? So next here, your task is to find all possible paths. See here, all possible paths are given, okay? So not maximize from some particular so paths or else minimization from the particular paths. Okay, that is the difference between so the DP and next of also the backtracking programs here. Okay, so all possible paths means we should go back and we should get the results from among all the in particular index we are going to get so the number of paths. In by traveling in different paths we are going to get the solution. Okay, we need to collect all those. Next. So the rat can take uh, to reach to the destination, okay, starting from 0, 0 and ending at n minus 1 and under the condition that the rat cannot revisit any cell along the same path, okay, this is very important thing, okay. So in the same path it should not travel here, okay, without traveling in the so same we should not revisit the same index. So for that sake, we are going to take one visited array. In most of the backtracking programs, so you are going to observe this, okay? For avoiding cycles, okay? Chances were there to move to the so cell again and again, so moves to the same cell, okay? So in order to avoid that, we are going to take extra visited matrix here. It's required, okay? So actually in graph programs, from graph programs onwards, so we observe like this, okay? Same thing you are going to observe here now. Furthermore, the rat can move only to adjacent cells that are within the bounds of the matrix, okay? Here, this is also very important. So we need to check whether it's crossing so the boundaries or not. Boundary conditions are very important here and not blocked. If no path exists, return an empty list, okay? And here, so you need to observe one more important point in this program. So that is return the final result vector in lexicographically smallest order. Means nothing but so ascending order, guys. Okay. So means here in the first example you can observe. So D means down, R means right. I hope you understood. Okay. It's given in the problem statement. L means left, and so up. U means up. Next. Say while moving sort of particular direction, so we need to add that particular character to the string. So finally, we are going to get some string. Okay, those strings we need to add to the some array, and that array we need to return from the so function. That is the problem statement here. So when compared to these two strings, okay, according to the lexicographical, which is smallest one, observe here. Here it's starting with T. This one all starting with T. But if you observe the next character here, okay. So in first string, so the second character is D, so here it's R based on this. So you can understood that lexicographically it's a smaller one. Okay. So means here at the time of generating recursive function calls also we should be careful. Okay. So to which direction? So we should generate first of all, you should remember this. This is very important here. So in this program, so that is in Geeks for Geeks program. Okay. Otherwise we are not going to get the correct answer. Remember this. So I clearly explained while taking some small example. Okay. I'll make use of the same example. With the help of same example, I'll explain. Don't worry. Next, observe the constraints here. Okay. N value lies in between 2 to 5. So very low values, right? So we are going to get so huge recursion tree even for small constraint also. For 4 by 4 also, you are going to observe that. That's why if for suppose n value is more than that means we are going to get TL errors here. Okay. Expected time complexity is here. Observe it's 4 power n by n. Means at each and every index we are going to generate some 4 recursive function calls. Okay. So that is allowed and auxiliary space extra. So 2 by 2 array we are going to take. I said visited array is required. So for designing so this program all this. That's why auxiliary space that is allowed, okay, and so it's from backtracking, guys, okay. So here relative related articles are given, okay. So means so we have n number of surroundings, capturing surrounding regions, okay. Likewise we have some programs in backtracking. All those programs you can understood with the help of so this knowledge, okay. So fine, this is so given solution class rat image function is given, and next of all, so the maze is given, guys. Okay. First of all, I'll explain. So the calling function part. Okay. Next of all, after completion of example, so example explanation, I'll design so the called function part. Okay. So what they asked actually, so to return some array of strings, right? Okay. So I'm taking one extra, so the result array here. Okay. To this result array, I am going to collect all the strings. Okay. Whatever I am going to generate, whatever the, or else let us take, no, okay, fine. What are the strings I'm going to generate? All those I'm collecting here. Okay, updated. So array I'm going to return here. Okay, so but before returning, okay, we need to call the function, right? So for calling function, so we need to take. what I said, with the help of so the visited array only, it is possible to design this type of programs, right? So I'll take one example here, so you can clearly understood why visited array is required. First of all, observe everyone. So this is the match. So we are going to work now. That is 1 0 0 0. Okay. Next, let us take a table. 1 minute. Let us take some bigger table here. 1, 2, and so 3. 1, 2, and so 3. 1 0 0 0, 1 1 0 0, 1 1 0 0, 0 1 1 1. This is the maze we are going to work now. Okay. Now current. So we are at this index. Okay. 0 0 index, guys. Okay. Now see, after moving, when so rat can move. So if cell is having so the one, right? Okay. So from here to here we can move. Okay, right? See, after this, so why can't so it can move from so this to here, okay? So again, move it can move to the upwards also, right? Okay. If so, cell is having so one at particular index, we are moving in so four directions, right? Okay. It can move towards the right. Okay, understood. It can move towards the down. Okay, right. But it can move towards the up also, right? If for suppose if it moves towards up, okay, what happens here? So here itself cycle forms. Okay. So in order to avoid it, so what we are going to do means, listen, we are going to take one extra visited matrix. Initially, we'll take all positions to zeros, but for clearly understanding so the explanation, I am going to take so this extra 2D array as empty. Okay, so empty 2D array I am taking. So clearly you can understood the explanation. Okay, 1, 2, and so 3. Okay, 1, 2, and so 3. So initially, actually, all memory locations are filled with zero, but now I'm not filling so the anything, right? Okay. So I hope she understood. So the purpose of taking so the visited. Okay. So later on, I'll explain how this visited. So matrix is helpful for so working with backtracking programs. Okay. So next, fine. First, let me complete so the calling function part. Okay. That is, I'm taking so the visited so array here. Initially, I'm taking so the zeros in all memory locations. So size I am collecting here in n variable. Okay, let us take n is equals to so the length of maze, guys. Okay, now observe the 2D array here. 0 for j in range of so n, and for I in range of so n. Okay, sorry. Okay, wait 1 minute. This one, it's let us take visited. This one, let us take so as a result array. Okay. So now let us so make a calling function. So function call. Okay. So we are in method, right? We need to call with self keyword self dot find path. I'm calling here. Okay. So what are required? So maze is required. We need to work with the 2D array. Okay. Next of all, so the visited array is required. So fine. Next of all, so the result array is required. In that only we need to store all the strings. Okay. And so initially I'm passing some empty string here to this string. So by the time of generating recursive function calls, so I'll add so particular call, particular character. Okay, and next, initially we need to start work from the 0 0 index, right? Okay, I and j positions are 0 and 0, and the size variable. So I'm passing here. Okay. So to work with the boundary conditions to check, okay, whether so the particular index crosses so the boundary or not. For checking that, so the n variable is required. That's why I'm passing here. I hope you understood why so all these are required. Okay, maze we need to work for avoiding cycles. We need visited, and for storing so the strings into the strings result array is required. Okay, and next, so we need to work with the different indexes, okay? And for checking boundary conditions, n is required. Next, let us go for defining so the called function here. So find maze visited result and empty string I am collecting in S here, okay? 0 0 I am collecting in IJ, and next of all, so n I am collecting so in n variable only, okay? So now let us start so working on it. So how to work with this? So observe this, everyone. Here, first of all, I'll explain one thing about the boundary conditions here, okay? So afterwards, I'll explain so the main logic. But suppose we are at ij position, guys. That is at 0 0 position. Okay. So or else don't consider some positions here. I and j. So we can move in four directions, right? We can move towards down. Okay. And we can move towards right. We can move towards left, and we can move towards up. Okay. From that particular index. So here on moving towards so down, okay. So what is the index we are going to get? J is fixed, right? So I is going to be incremented. The row value is going to be incremented, and so the column index remains same. So here at the time of so checking, so if we are at the index, we should check whether so the downside downward index position so value is one or not in the maze, okay. Uh, so, or else we should check whether some particular position is visited or not in the visited matrix. So, what we need to do here is at the time of generating this recursive function call, we should check whether so I plus 1 is still if it is less than of n or not. Then only we should go for generating recursive function call. Okay. Might be because of generating so the recursive function call. So, 1 minute. So here might be by the time of checking, so the downward cell might be we may reach to the n position, right? At that time, it is not possible to check, and we may get index error. Okay, so that's why if I plus 1 is less than of n, then we should go for checking so that particular position. I hope you understood. So likewise, we should check for so the four constraints here at the time of checking. If you want to check the right side cell, okay. So here, what happens? I remains same. J becomes increment, right? We should check whether so j plus 1 is if it is less than of n, then only we should go for checking so that particular position value. Likewise, so if you are generating recursive, if you want so to compare, to check with the previous index value, okay? What indexes we are going to get? I minus 1, comma. So j remains the same, okay? Sorry, 1 minute. So I remains the same. J is going to be updated, right? So we should check whether so the J reached to the so negative index or not. If j is greater than or is equals to 0, then only we should make so comparison. So then only we should go for checking whether that cell contains a 1 or not. Okay. Likewise, so here also we need to focus. So I minus 1 previous row and column remains same. We should check whether so I is greater than or is equals to of 0 or not. Then only we should go for so checking this. Okay. Hope you understood. With these four conditions, we'll start making comparisons now. Okay, so fine. I hope so you understood. So how we are going to work now. Okay. So fine. So let us start now. So we are at 0 and 0th index, and initially, so we have some empty string. Let us take so here we are at 0, 0 index, and we have some empty string. Okay, with us, and so we can move in these directions, guys. Okay, so that is what is the according to the lexicographical so order we need to print the results, right? Okay, we need to traverse here. We need to generate the recursive function calls. Okay, so what is the first thing we need to get? D means down. Okay, and so the next one is left according to the alphabets. Okay, next one is L according to the alphabets. Next one is right according to the alphabets. Next one is U. Okay, if you generate recursive function calls according to this order, okay, we are going to get lexicographically so increasing order strings, guys. Okay, so fine. We are at this particular index now. So check. Now we are at this index now, 0, 0. So check whether, what is the first one? We need to check downward, whether it's possible to move downward or not. Okay. Yes. So why not? Because so first position is 0, 1 position is pointing to the 1, and that too that cell is so not visited here. This is empty. Observe here. So this is empty here. So we can move. So here, so by the time of so moving to the so this cell, what you need to do here is we visited so this cell, right? We should mark this. So in the visited cell means we should change that particular position to 1 actually. So but for clear understanding, I am taking so check marks and cross symbols here. Okay. So we should so consider 0, 0 position. We should take it as visited. Okay. And so afterwards, we should generate recursive function call for 1 and 0. And at the time of generating recursive function call, so we are moving towards a downward only, right? So we should take like this. D character we should append to the empty string. Okay. So again at this for this particular function, so we have 4 directions. Okay, possible. So again, we need to check whether so the downward direction is possible or not. Okay. Yes, again, it's possible because this cell contains so 1 which is not blocked. We can move, and that too. So that particular cell is not visited. Okay. Yes. So then what we can do now? Current index, we can listen my explanation carefully now. Okay. With this explanation, you can understood program better. Okay. So directly you cannot understood so the program better, and it's not possible to remember also. Listen my explanation properly. Current index I am marking as visited, and I am generating so the recursive function call for 2, 0 position. Okay. And so again we are moving towards the downward direction, right? Again to the previous string we should append so the D. It becomes so the DD. Okay. Hope you understood so how we are going to get so the result string now. Again at this particular index we have some 4 possibilities here. Okay. So D, L, R, U. Now, is it possible to move to this position here? 3, 0. No. Downward direction is not possible here because that cell is blocked. Okay. Is it possible to move towards left? Okay. No, it's not possible because we are going to get negative index. Okay. That's why we are going to check whether is it possible to move to the left or not. If it is not greater than or is equals to 0 means we cannot move. We are not going to generate recursive function call. Simply we are going to avoid. Okay. And the next, so let us check whether right side is possible or not. Yes, right side is possible because, sorry, not here, here. Left side is not possible. Okay. Right side it's possible, guys. Now, it is possible because this cell contains so the 1 here. Okay. So means what I said. If it is possible and if it is not visited here, so check it's not visited that position. So now current current position, we should mark it as visited in visited array. And after that, we should generate recursive function call. So to that position, 2, 1. Okay, 2, 1. And so to which direction we are moving? So towards the right side, right? So we should add like this, D, D, R. Okay, we should append so the character R here. So again, at this position, so we have these possibilities downward, so the left side, and next of all, so the right side, and towards upward. Okay, so fine. Now again, let us check whether it's possible to move towards downward direction or not. Right? Yes, it's possible because the downward cell is parked as 1 and it's not visited here. Okay, so fine. We can move it. So we can generate a recursive function call. So for 3, 1 position, we are moving towards downward direction, right? So means what we need to do? We should append a D character here once again, okay? And by marking current cell as marker, so visited, we should generate recursive function call to here. So fine, again at this index we have so these possibilities, okay? D, L, R, U. Next. So fine. Now let us check whether it's possible to move towards downward direction or not. No, it's not possible. Okay. So because on moving towards the downward direction, so we reach it to the n value. Okay, which we are crossing the boundary. Next. So is it possible to move towards the left side here? No, because this is blocked. No, it's not possible. Next, is it possible to move towards right? Yes, right is possible because so this cell is pointing to the one. Okay. Next of all, it's not visited here. Okay. So fine. After that, what I said, current position we should mark as visited, and we should generate recursive function call towards the right. Okay. By the time of generating function call towards the right, okay, we should take so R, D, D, R, D, and so R it is. Okay. Again, so at this particular position, so we have 4 direction. We can move in 4 directions here. Okay. So again, downward is not possible because now listen here. You are going to observe clearly what is the use of visited. Okay. Visited array. Downward it's not possible because we are going to reach to the n value. Okay. So next. So left side, is it possible? Yes, because see here this cell is visited. So this cell is marked as 1, right? Okay. This cell is containing value 1. But we are not going to move because this is already visited. Okay. So if it is already visited, we are not going to move to that index because we are going to get cycle now. Listen. So again, it moves to here now. So again it moves to here and afterwards again it moves to here. So there itself it is going to be stopped. Okay, that's why to avoid so the cycles. Okay, we taken visited list. I hope you understood now clearly what is the usage of this. So left side, no, it's not possible, and right side is let us check. It's possible because so the last cell, okay, it's marked as 1 here. Next, what we can do? Current cell we can current cell we marked as visited, and we are going to generate recursive function call towards the right. Okay, so 3 comma 3, and we are moving towards the right, right. Okay, D or DDR DRR. Okay, this is the string. Finally, we are going to get whenever so we reach it to the so size minus 1. Okay, n minus 1, I variable and j variable reaches to the minus 1. We are going to collect so that string. So that string we are going to collect into the result array. Okay, and next so we need to perform so the backtracking operation. So because so the thing is we need to get so all possible paths we need to print here. Okay, so that's why we should backtrack here. I hope you understood. So how we are getting so the first result here, and now we need to remember one important thing here while backtracking. So you need to convert so the current visited so the positions to the so zeros. Okay, Earlier, so by the time of visiting, we marked as 1. By the time of backtracking, we should again marked as unvisited. Okay. So now listen. Again, by the time of moving to the 3-2 position, so what I am saying here is, okay, we should mark so this one as unvisited. Okay. Because again we move to the 3-2 position. Now let us check whether is it possible to move towards upward direction or not. In this position, is it possible to move towards upward? No, because it contains so the 0 here. Okay. No, it's not possible to move towards the upward direction. All directions we observed here. Okay. Second, while moving to the 3-1 position to the, so sorry, this one. It is not possible upward here. While moving to the 3-2 to 3-1 position, first 3-1 position we should mark as unvisited. Okay. Afterwards, we can move to that particular position, 3-1. Okay. Again, so here we have 4 directions. Already 3 directions completed. One direction is remaining, so that is upward. Okay. So fine. Upward direction. Right. Upward direction. So it's actually pointing to the so 1 and it's already visited. Okay. So what I said. So while moving to that particular position, we should mark as so unvisited, right? Okay. So yes, observe. It's already visited, right? So observe this. It's already visited. That's why we should. So it's not possible to move towards upward. All directions are completed. Next of all, so while backtracking to the 2-1 position, we should mark first of all 2-1 position as unvisited. Okay. Afterwards, we should move to that position. Now in this position, we have 3 more directions are remaining: left, right, and next of all, so the up. Okay. So left direction, it's not possible because it's already visited. Okay. Left is not possible here. Right is also not possible because that position is marked with 0. In maze, you can check here. So right is not possible. Sometimes based on visited list, we are going to avoid moving to the particular cell if it is already visited. And sometimes so we need based on this. If maze position is marked as 0, we are going to avoid it. So, but now check whether it's possible to move towards upward direction or not. Yes, it's possible because, so here check everyone. This position is not marked. So this is actually marked as unvisited only, right? There is no check mark. Okay. So in that, so we can so move to there. Okay. So while moving to that particular position, so what we need to do, we should make so the current cell marked. Okay. So fine. So observe carefully, everyone. Now upward direction we can move. So here one more path we are going to get function call of. So have a look. That is 1 comma 1. We are going to reach to this position, guys. Okay. 1 comma 1. Remember 1 comma 1. Next of all, so we are moving towards upward direction, right? To this particular string, we should add so u. DDRU is the current string. Again, in this position, so we can move towards downward, so left side, right side, and towards upward. Okay. So, but now let us check. We are at this index, guys. Okay. So left side, it's not possible because already it's visited. Okay, you can check here. It's visited here. Next, upward. See, downward. It's not possible. First of all, because downward is visited. Okay. Next of all, left side is not possible. It's visited. Okay. Right side is not possible because it's blocked. Upward is also not possible. It is blocked. Okay. Because so now here clearly you can understood one thing. Okay. So all these 4 directions are not possible at this particular position. Okay. So we are not going to reach to the n minus 1 and n minus 1 position, and there is no use of it. Okay. So what we need to do now? Now we should move to the 2-0 position, right? Before moving to the 2-0 position, we should make current cell as marked, unmarked. Okay. See, observe how many times we are marking and unmarking. So observe carefully, everyone. 2-0 position, right? Okay. While moving to the 2-0 position, 2-1 position, so we marked as unlisted. So here in this position, so we taken all this downward, left side, right side completed. Upward, is it possible? We are at this index, guys. Already upward is so visited. Okay. So now not possible here. Okay. All directions are completed. Before moving to the 1-0 position, first 2-0 position, we should mark as unvisited. Okay. Next, so now we are at 1-0. So still three more directions are remaining here. So that is left side, right side, and next of also towards upward. Left side, it's not possible because on moving towards the left side, we are going to reach the boundary. Okay, we'll get the negative index. Left side, not possible. So the right side is possible to here as it's possible because it's not visited. Okay, and that too. So this position is filled with one. Why can't? As we can so fill here from here onwards. So we are going to get so the another path. Okay, so that path so here we are going to get so the another path with the position so called 1 1 and so moving towards the right side direction, right? Okay, so right side direction, so that is dr is going to be attached to the string. Okay, afterwards we'll start from that position onwards we'll start so the working here. So d of function of 1 comma 1 position and next of all so downwards and towards the right side direction. So again at this particular index we have four possibilities: downward, so towards the left side, and so towards right side and towards upward. Okay, now we are currently at this index. Okay, next so we check whether it's possible to move towards the downward or not. Yes, it's possible because it's not visited. Okay, so we can move to there. So means what we should do? Current index we should first of all in visited array. First of all, we should mark current index as visited, and we can move towards downside here. Okay, downward. Let us finish this. F of so 2 1, and we are moving towards downside, right? Okay, downwards we moved down, left, and next of all, so the right upward. So again, we need to check whether it's possible to move towards the downward or not. Yes, again, it's possible because it's marked as one. While moving to the next cell, okay, downward cell, we should mark this one as visited here. Okay, yes, we should mark that one as visited, and we should generate recursive function call here towards the downward. Okay, f of 3 1, and next of all so we move towards the downside, right? Okay, downward again at this index we have some four recursive function calls. Okay, downward, left side, and right side, but downward this time not possible because we are going to reach to this boundary here. Okay, next, what is the next one we have? So the left is also not possible because observe here left side it's blocked. Okay, in the maze it's blocked here. No, it's not possible. Next, right side, yes, it's possible because observe here it's not visited here. It's marked as unvisited. Okay. And next to the in maze matrix, actually it's filled with one. Okay. What you can do again, you should mark it current index. You can mark as visited, and you can move towards the right side. Okay. So while moving towards the right side, what we should do? Uh, we should add R character to the string. Okay. So downward, leftward, right side, upward. So these are the possible directions. So we have next. So again, downwards is not possible because we are at last row. Okay. Left side is not possible because currently we came from the same index. Okay, it's already visited here. So based on this one, you cannot move. Okay, so right side as it's possible to move because it's filled already. So it's not visited. Okay, and so sorry, it's not visited, and next of all, it's so filled with one. Okay, current index we should mark it as visited, and we should move to there. Okay, so finally we got one more answer here, reach to the 3-3 position. So that is DR. Okay, DDRR. Okay, so this is the thing we need to do, and again it is going to perform. Okay, but we are not going to get another any other results. Okay, so it backtracks upward. It is not possible. Okay, again it backtracks upward is not possible because blocked. It is going to check, but we are not going to get any results. Okay, apart from these two. So it is going to mark so those cells as unvisited once again. It moves to there, so left side not possible, right side not possible, upwards so not possible. And again, it moves to there, both left side, right side, upwards, so all those are not possible. Finally, so it reaches to here, okay, in 1-0 position, so it's not possible to move towards 1-0 position. It's not possible to move towards upward because already visited. So finally, after reaching to here, it is going to be stopped. Okay. Left side is not possible, right side is not possible because it's blocked, left side moving. Okay. It reaches to the boundary. Next, so upward is not possible. Final, see, for the first cell, so the remaining directions is going to be checked at the ending. Okay. See, I explained up to the ending. So I did just explain so the two parts here up to the ending. So how it's working explained here. So by taking some recursion tree and next of all, so the visited matrix, input matrix, all this, you are going to understood all the remaining programs. I told you capture surrounding regions. Okay. N-Queens program, all this you can understood like this, guys. Okay. See, you are already observing how much time it's taking. Okay, so for explaining one program and for understanding, okay, we don't have so the enough time, so you need to gone through the programs based on these models. Okay, fine. I hope you understood. Now let me complete. So solution of this one. First of all, we need to focus on direct generating downward, okay, function call, right? Downward means so row index increments, right? While incrementing row index, okay, before going to generate a recursive function call for downward direction, first we should check so whether on generating so function call for downward direction, whether it reaches to the n or not. If it is not reaches to n, then only we should go for generating recursive function call towards down. Okay. So this is the condition we are using initially for checking before going to generate recursive function call towards downward. Okay. So and we need to check a few more things. If already downward cell is visited, okay, again we should not so go for so that particular memory location, right? Okay. So observe this. If it is if visited of downward cell, I hope you understood. I plus one, so J means downward cell. We are checking whether if it is not visited. If it is not visited and on generating on moving towards downward, if we are not going to reach to the n, okay, and in the mage input matrix, okay, if downward cell is marked as one, then only it's possible to move to that particular cell, right? Okay, so observe here, I'm taking mage of I plus one, and so j if it is pointing to the one. I hope you clearly understood this. Okay, on moving towards downwards, okay, if we are not going to reach n, and so if downward cell in the visited so matrix is not visited, okay, if it is pointing to the zero, and next of all, So in the match input matrix, downward cell if it is filled with one. What I said, current cell in the visited matrix. First of all, we should make it as market, right? Same thing I explained. So that's why I said. So with the explanation, you can understood this one clearly. First of all, so the current cell. See, I'm not taking I plus one here. So the current cell means ij. Okay, 0, 0 position cell. First of all, so I marked as one. Afterwards, so I generated function call for so the downward cell. Okay, while generating function call for the downward cell, so I added so D character to the result, so the string, right? So observe now, everyone. I forgot to take self here. Okay, so let us take self dot. So find of match, comma visited. Okay, comma result, and to the string. So what I'm doing here, I'm adding so the D. Okay, so D character I'm appending here. Next, so we need to update. We should generate recursive function call towards the downward cell only, right? Okay. So I index only we should update. So there is no change in the so J index now. Okay. So I plus one remains same. So J I am update. So passing as trees, and there is no change in the N also. Okay. And so you observe this after completion of getting some path, okay, while moving towards the backward, okay, what you need to do after completion of generating this function call, we are going to get some path you observed, okay. We need to backtrack, right? While backtracking, what I said again, so the current position, so cell, we should mark it as unvisited, okay. This point is very important here. This is the change you are going to observe. So in backtracking programs, so similar model you are going to observe in the rest of the programs also you are going to observe the similar model. Okay, so fine, I hope you understood. So this likewise, let us finish so the remaining here first. After downwards, what I said here, this is very important. Order of generating recursive function call. Next of all, we should generate recursive function call for the left side, right? Okay. So that is if j minus 1, left side means column, so becomes the column moves towards left side, right? Okay. Row remains same. So if column is greater than or is equals to 0, and so the same thing. If that previous column position is not visited and in maze, see, I'm typing so the all four, I'm not just copying and making changes here, okay? And if maze input matrix, if that position is pointing to the one, okay, so then current, so the cell we can mark it as visited, okay, generate function call for the left side position, but while generating so function call for the left side position, we should add L. Okay. So to the string here, next, so I remain same. We should generate recursive function call to the previous column here. Okay. And while backtracking, so the same current index, so we should mark it as unvisited. Okay. So by updating to the 0. I hope you understood. Now, likewise, let us check for remaining here. Okay. Next, what is the next one? So right side direction, right? J plus 1 if it is less than n, and so visited of I and j plus 1 if it is not visited, and next of all, so the maze of I and j plus 1 if it is pointing to the 1, then we can move to there. First of all, so the current index 1, we should mark it as visited, and afterwards we should generate recursive function call. So towards the right side, that's why I'm adding or, okay, to the string. I remains same, I'm generating function call for j plus 1 here, okay, and also remains same. While backtracking, so the current index we should mark it as so the unvisited, okay. See, after seeing permutations of string, all this, okay, might be you feel easy of this one, okay. Might be by seeing some 2 hour programs, but here because of not having time directly, I'm explaining this, okay. So that's why I just gone through those programs at once so that clearly we are going to understand that one and this one also, okay. So fine. And finally, let us take so this. upward direction, I minus 1 or row value changes, right? If it is greater than or is equal to 0, and if not visited, and next of all, if that particular position is pointing to the one, yes, we can mark it as visited first of all, and we should generate recursive function call. And while generating recursive function call, we should add a u character, okay, to the string. And we should generate function call for I minus 1 position. J remains same and n remains same, okay. So these are the four function calls, okay. You can observe at any particular index. At particular index, you are going to observe four directions: downward, left side, right side, and upward. So finally, for suppose if I and so j reaches to the n minus 1 and next of all, so the n minus 1. In that scenario, as should collect into the so result array here. Result dot append of yes. Afterwards, we should control return back to the previously generated recursive function calls. Actually, remaining all directions has to be completed for each and every recursive function call, right? Okay, we should generate. We should take return here. Okay, I hope you understood the usage of return. So whatever the updated array here, so whatever the array updated there, so will be returned here. This is acts as call by reference, array acts as call by reference. Whatever the strings we are adding there will be returned here. So let us check whether compiling and run, whether it works or not. Okay, base case failed. Wait, I think I did some small mistake. 1 minute, I'm so checking monitoring. So where mistake happened. Mm. Sorry, here visited. So this one current position mark visited as visited, and so I forgot to update this one also while backtracking. So that current index we should mark it as unvisited, right? Sorry, I forgot this. Fine. Now check everyone. So the base let us submit now. Let's check. So the all test cases are passed here. Okay. So it just taken some 0.04 milliseconds. Okay. So I hope so it's clear for everyone. Okay, so just gone through for 2 minutes now. It's not possible to discuss so the remaining programs also. I hope so you have got some knowledge how much time it taken. It's not possible to discuss so the next ones. So that's it for today's session. I hope so you understood this. So all the best so for Hack with Infy, okay, exam. So gone through the model program. So based on this, if possible, so I think CSC students have knowledge on data structures, right? Okay, gone through stacks, queues, trees, and graphs. So programs also. Linked list programs are actually not asking, and so gone through just regular programs of arrays and strings also. That is two pointer or else hash table approach programs. Okay, still we didn't discuss it that. So, but gone through that if you have so the knowledge on it after that, and don't forget to focus on this. Okay, DP backtracking, so the greedy bit manipulation. Okay, Mm, definitely you are going to get so the coding questions on this. Okay, still I think so. One more day is remaining. Okay, so try to give the best. Okay, so all the best. So to everyone. Okay, that's it. Thank you everyone.